4.5 billion years ago, in a quiet corner of the Milky Way galaxy, something catastrophic is about to happen. A collision so violent, so impossibly destructive, that it will forge the very ground beneath your feet. This wasn't some gentle cosmic assembly. This was war, pure, unfiltered chaos on a planetary scale. The Earth you're standing on right now, it shouldn't exist. Not like this. Not with a moon. Not with oceans. Not with you. Every single atom in your body passed through cosmic violence so extreme that it defies imagination. And scientists are only now beginning to piece together just how brutal Earth's birth actually was. Understanding how our planet formed isn't just about the past. It's about understanding whether worlds like ours are common in the universe, or whether we're the product of a cosmic accident so rare that we might be utterly alone. The story of Earth's creation is written in violence, and that violence may hold the key to whether life exists anywhere else in the cosmos. To understand Earth's violent birth, we have to go back, way back, to a time when our planet didn't exist at all. Just a swirling disk of gas and dust orbiting a newborn star we call the Sun, the solar nebula. This disk contained all the raw ingredients that would eventually become the planets, moons, and asteroids of our solar system. But how do you get from a cloud of dust to a planet? The early solar system was nothing like the orderly arrangement of planets we see today. It was a demolition derby, a cosmic shooting gallery where collisions were the rule, not the exception. Picture it. Thousands, maybe millions of rocky bodies careening through space, smashing into each other at speeds that would vaporize anything we know today. Tiny dust grains begin to stick together through static electricity, like cosmic Velcro. These clumps attract more material through gravity, growing bigger and bigger. These are planetesimals, the building blocks of planets. Some are the size of mountains, others the size of cities, and they're all on collision courses with each other. When two planetesimals collide, it's not a gentle merger. The impact releases energy equivalent to millions of nuclear bombs. Rock vaporizes instantly. The heat is so intense it creates a molten sea of liquid rock. But instead of destroying everything, these violent collisions actually help planets grow. The debris from the impact doesn't fly away into space. Gravity holds it close and it rains back down onto the growing protoplanet, adding to its mass. This process repeats thousands of times, millions of times. Each collision adds more material, makes the gravity stronger, attracts even more objects. It's a runaway process. The bigger you get, the faster you grow, and in just a few million years, less than 1% of the age of the universe, these violent collisions have created dozens of planetary embryos throughout the solar system. One of these embryos, orbiting at just the right distance from the Sun, is proto-Earth. Not quite the planet we know, but getting there. At this stage, Earth is probably about 90% of its current mass. It's a hellish world. The surface is an ocean of molten rock, heated by the constant bombardment of impacts. There's no atmosphere as we know it. No water, no life, just an inferno of liquid stone. But proto-Earth's growth is about to be interrupted. Something is approaching through the chaos of the early solar system. Another planetary embryo, orbiting in a slightly different path. Scientists call this world Theia, named after the Greek titan who gave birth to the moon goddess Selene. And the name is prophetic because what Theia is about to do will literally give birth to Earth's moon. Theia is roughly the size of Mars, about half the diameter of Earth, maybe 10% of its mass. In cosmic terms, it's Earth's sibling, born from the same disk of dust and gas. For millions of years, Theia and proto-Earth orbit the Sun without incident. But orbital mechanics are tricky. Subtle gravitational influences from Jupiter and Saturn slowly alter these orbits, nudging them, changing them. Until one day, the inevitable happens. Theia's orbit intersects with proto-Earth's. The two planets are on a collision course. There's no escaping it now. In the final hours, any observer would see two glowing worlds, each with a surface of molten rock, drawing closer together. The gravitational pull between them accelerates both planets toward each other, faster and faster until they're moving at 15 kilometers per second. That's 33,000 miles per hour. And then, 4.5 billion years ago, they collide. The impact is beyond description. In a fraction of a second, Theia slams into proto-Earth at an angle. Not head-on, but a glancing blow that tears both worlds apart. The collision releases energy equivalent to billions of nuclear weapons detonating simultaneously. The temperature at the impact site reaches tens of thousands of degrees. Hot enough to vaporize rock instantly. Hot enough to turn solid iron into gas. Theia's core, made of molten iron and nickel, punches deep into proto-Earth's mantle. The shockwave ripples through both planets, shattering their structures. Massive chunks of both worlds are blown into space. Some escape the gravity well entirely and are lost forever. But most of the debris stays in orbit, forming a ring of vaporized rock and molten droplets around what's left of Earth. This ring is incredibly hot, glowing white-hot. It would outshine the sun itself if viewed from space. The debris particles are moving at incredible speeds, colliding with each other, sticking together, breaking apart. It's chaos. Pure, unfiltered cosmic violence. And from this violence, something remarkable is about to form. The day after the impact, if you could call it a day, Earth is unrecognizable. What remains of our planet is a spinning ball of molten rock, glowing like a second sun. The surface temperature exceeds 2,000 degrees Celsius, hot enough to melt iron. The entire planet is an ocean of magma thousands of kilometers deep. There are no continents, no oceans, no solid ground whatsoever. Earth is literally a droplet of liquid rock floating in space. Above this hellscape, the debris ring stretches across the sky. Billions of tons of vaporized rock and molten droplets orbit Earth, creating a spectacular and terrifying sight. This ring is gravitationally unstable. The particles are colliding constantly, and through these collisions, something incredible is happening. The ring is beginning to clump together. Scientists call this process accretion. It's the same process that built the planets in the first place. But this time, it's happening incredibly fast. Within just a few years, maybe even months, the debris ring begins to form a single large object. A new world, born from the violence of the impact. We call it the Moon. The Moon forms at a distance of just 25,000 kilometers from Earth. Today, it sits at 384,000 kilometers away. That means the newborn Moon is 15 times closer than it is now. From Earth's molten surface, the Moon would fill a huge portion of the sky, appearing 15 times larger than the Moon we see today. It's an absolutely massive presence, dominating the heavens. And that proximity has consequences, enormous consequences. The gravitational pull between Earth and the Moon at this close distance is immense. The Moon's gravity creates tides in Earth's magma ocean. But these aren't the gentle tides we experience today. These are megatides, enormous bulges in the molten surface, hundreds of meters high, that sweep around the planet twice a day. The Moon is also spinning much faster than it does today. A day on the newborn Moon lasts just a few hours. The Moon is tidally locked to Earth almost immediately, meaning the same side always faces Earth. But Earth itself is spinning incredibly fast. A day on post-impact Earth lasts just 5 hours. Our planet is rotating so quickly that the magma ocean is stretched into a slight bulge at the equator. This rapid rotation creates intense weather patterns in what little atmosphere exists. Supersonic winds tear across the surface at thousands of kilometers per hour. The heat from the magma ocean creates massive convection currents, stirring the molten rock like a global mixing bowl. It's a vision of hell beyond anything we could imagine. But there's a problem with this picture. Scientists have analyzed moon rocks brought back by the Apollo missions, and they found something completely unexpected. The moon's composition is almost identical to Earth's mantle. Not just similar, almost exactly the same. The ratio of oxygen isotopes, the mixture of different elements, it all matches Earth perfectly. This is really weird. Theia came from a different part of the solar system. It should have a different composition, different isotopes, different chemical signatures. When Theia and proto-Earth collided, the moon should have formed mostly from Theia's material, and that means the moon should look chemically different from Earth. But it doesn't. It's like Earth and the moon are twins, formed from the exact same material. For years, this isotope problem haunted scientists. How do you get the moon to be made of Earth material when it formed from a collision with another planet? Some scientists suggested maybe Theia just happened to have the exact same composition as Earth. But the odds of that are astronomically small. It would be like winning the lottery a million times in a row. Other scientists proposed different collision scenarios. Maybe it wasn't a glancing blow. Maybe Theia hit Earth head-on, completely vaporizing both planets. The resulting debris would be mixed so thoroughly that the moon forming from it would naturally have Earth's composition. But this scenario has its own problems. A head-on collision would impart too much energy, potentially destroying both planets entirely. Then, in 2015, a team of scientists ran sophisticated computer simulations of the giant impact. They used supercomputers to model the collision in unprecedented detail, tracking millions of particles through the impact and its aftermath. And what they found changes everything we thought we knew about Earth's formation. The simulations revealed that during the impact, Earth and Theia don't just collide and separate. They merge. For a brief period, perhaps just a few hours, the two planets become one spinning, churning mass of vaporized and molten rock. Scientists call this a synestia. It's a new type of planetary object, a donut-shaped cloud of vaporized rock surrounding a molten core. In a synestia, the material from both planets mixes completely. The violent churning stirs Earth and Theia material together until you can't tell which came from where. It's like mixing two different colored paints. Once they're combined, you can't separate them again. And this mixing solves the isotope problem. The moon forms from the synestia, which contains thoroughly mixed material from both Earth and Theia. That's why the moon has Earth's chemical signature. The synestia doesn't last long. Within a century, maybe less, it cools and condenses. The moon forms from the outer edges of the synestia, while Earth reforms at the center. As the synestia collapses, it rains molten rock. Droplets the size of mountains fall from the sky, splashing into the magma ocean below. The energy released by this rain keeps Earth's surface molten for millions of years. But the giant impact didn't just create the moon. It fundamentally changed Earth in ways that made life possible. Before the impact, proto-Earth probably had a thick atmosphere of hydrogen and helium, like a miniature version of the gas giants. The impact was so violent that it blasted this primordial atmosphere completely away into space. Gone. Removed in a single catastrophic event. This turns out to be incredibly important. That hydrogen and helium atmosphere would have been useless for life. It would have created a massive greenhouse effect, making Earth too hot for liquid water. By stripping away this atmosphere, the giant impact gave Earth a fresh start. A chance to build a new atmosphere from volcanic gases, an atmosphere that could eventually support life. The impact also did something else, something that would prove essential for life. It tilted Earth. Before the collision, proto-Earth probably spun upright, its axis perpendicular to its orbit around the Sun. But Theia's glancing blow knocked Earth sideways, tilting our planet's axis by 23.5 degrees, and it's stayed tilted ever since. This might seem like a minor detail, but it's anything but. That tilt gives Earth its seasons. Without it, the equator would be scorching hot year-round while the poles remained in eternal frozen darkness. The temperature difference would create permanent, violent superstorms that would make the planet nearly uninhabitable. The tilt, this gift from cosmic violence, makes Earth's climate stable and predictable, perfect for life. But in the immediate aftermath of the impact, life is the furthest thing from possible. Earth remains a molten nightmare for millions of years. The magma ocean slowly cools, but it's a gradual process. Heat has nowhere to go except out into space through radiation, and that takes time. Lots of time. Lots. Eventually, about 10 million years after the impact, something remarkable happens. The surface begins to solidify. Not all at once, but in patches. Islands of solid rock form on top of the magma ocean, floating like icebergs on a sea of molten stone. These proto-continents don't last long. They're constantly recycled, melting back into the magma, only to reform somewhere else. But their appearance marks a turning point. Earth is beginning to develop a crust. As the surface cools further, volcanic activity explodes. Thousands of volcanoes erupt simultaneously across the globe, spewing gases into the sky. Water vapor, carbon dioxide, nitrogen, sulfur compounds. These gases form Earth's second atmosphere. It's nothing like the air we breathe today. There's no oxygen. The atmosphere is thick with carbon dioxide, making it a toxic, choking environment. But it's an atmosphere, and that's progress. Within this new atmosphere, water vapor begins to condense. Clouds form for the first time in Earth's history. And then, perhaps 100 million years after the giant impact, something happens that will change everything. It starts to rain. But this isn't a gentle shower. This is a deluge of biblical proportions. The rain that falls on early Earth continues for thousands of years, maybe millions. Water pours from the sky in endless torrents, so heavy that visibility would be measured in centimeters. The sound would be deafening, a constant roar that never stops. This is the longest storm in Earth's history. As the rain falls, it collects in the lowest points on the surface. Craters from ancient impacts become the first lakes. Valleys between volcanic mountains become rivers. And slowly, inexorably, these bodies of water merge and grow. Within just a few million years, Earth has something it's never had before: oceans. But there's a problem. A big problem. Scientists have calculated how much water vapor Earth's early volcanoes could have released. And it's not enough. Not nearly enough to fill Earth's oceans. The volcanoes could maybe provide 10% of the water we see today. So where did the rest come from? The answer lies in space, and it involves more cosmic violence. Beyond the orbit of Mars lies the asteroid belt. Billions of rocky bodies, remnants from the solar system's formation. Most asteroids are bone dry, just bare rock and metal. But some, particularly those in the outer asteroid belt, contain significant amounts of water ice. And in the chaotic early solar system, many of these water-rich asteroids are flung toward the inner planets. Earth, with its growing gravity, acts like a cosmic vacuum cleaner. It sweeps up everything in its path. And for hundreds of millions of years after the giant impact, asteroids rain down on our planet. Some are small, burning up in the atmosphere. But others are huge, kilometers across. When these monsters hit, they explode with the force of millions of nuclear weapons. Each impact creates a crater hundreds of kilometers wide. The shockwave levels everything within thousands of kilometers. If there were any primitive continents forming, these impacts destroy them, melting them back into the crust. The heat from these collisions vaporizes the water the asteroids brought with them. But that water doesn't escape. It joins Earth's atmosphere, eventually raining back down to add to the growing oceans. This process repeats millions of times. Asteroid after asteroid slams into Earth, each one delivering a payload of water. It's violent, it's destructive, but it's also generous. These cosmic deliveries are filling Earth's oceans, drop by drop, impact by impact. Without this bombardment, Earth would be a dry, barren world. Life as we know it couldn't exist. But asteroids aren't the only things hitting Earth. Something even more exotic is delivering water to our planet: comets. These icy wanderers from the outer solar system contain vast amounts of frozen water. When Jupiter and Saturn formed, their massive gravity flung countless comets toward the inner solar system, and many of them found Earth. A comet impact is different from an asteroid impact. Comets move much faster, traveling at speeds up to 70 kilometers per second. That's 150,000 miles per hour. When a comet hits Earth at this speed, the energy released is staggering. A single large comet impact could deliver as much energy as 100 million nuclear bombs. The explosion would be visible from the other side of the planet. These comet impacts are so energetic that they can actually blast away parts of Earth's atmosphere into space. It's a cosmic irony. The very objects delivering water to Earth are also stripping away the air. But Earth's gravity is strong enough that it holds on to most of its atmosphere, and the water from the comets more than makes up for what's lost. Scientists have analyzed the hydrogen in Earth's oceans and compared it to hydrogen in comets. They're looking for deuterium, a heavy form of hydrogen. Different parts of the solar system have different ratios of regular hydrogen to deuterium. It's like a fingerprint that tells you where water came from. And what they found is surprising. Most comets have too much deuterium. Their deuterium ratio doesn't match Earth's oceans. This suggests that while comets probably contributed some water, they're not the main source. The bulk of Earth's water likely came from asteroids, but there's a specific type of asteroid that matches Earth's water signature almost perfectly: carbonaceous chondrites, primitive asteroids from the outer asteroid belt that contain up to 20% water by weight. These asteroids are the unsung heroes of Earth's story. Without them, our planet would have maybe 1/10 of its current water, just enough for shallow seas, not the deep oceans we have today. The violence of the early solar system, the chaos that flung these asteroids toward Earth, is directly responsible for the oceans, for the water in your body, for every drop of rain that's ever fallen. But the bombardment isn't over. Around 4 billion years ago, about 600 million years after Earth formed, something catastrophic happens in the outer solar system. Jupiter and Saturn, still migrating through the solar nebula, enter into a gravitational resonance. Their orbits align in a way that amplifies their gravitational influence on each other. This triggers a massive instability. The ice giants, Uranus and Neptune, are thrown into chaos. Their orbits change dramatically, and as they migrate, they plow through the Kuiper Belt, a region beyond Neptune filled with countless icy bodies. It's like kicking a hornet's nest. Billions of comets and asteroids are flung in every direction. Many are ejected from the solar system entirely, but many more are sent careening toward the inner planets. This event is called the Late Heavy Bombardment, and it's the most violent period in Earth's history since the giant impact. For 200 million years, Earth is pummeled relentlessly. Impacts happen daily, weekly. The surface is cratered beyond recognition. Any crust that had begun to form is destroyed and reformed multiple times. The oceans themselves might have been boiled away and then replenished by subsequent impacts. The evidence for the late heavy bombardment is written on the Moon. Without weather, without plate tectonics, the Moon's surface is a perfect record of the early solar system. And it's absolutely covered in craters. The large, dark patches we see on the Moon, the Maria, are actually enormous impact basins filled with ancient lava. These basins were carved out during the late heavy bombardment by asteroids tens or even hundreds of kilometers across. If the Moon took this beating, Earth took it worse, much worse. Earth's gravity is 6 times stronger than the Moon's, meaning it attracts far more projectiles. For every impact on the Moon, Earth probably suffered 20. The violence is almost incomprehensible. Impacts large enough to vaporize entire oceans, to melt the crust down to the mantle, to send shockwaves through the entire planet. And yet, paradoxically, this violence might have been exactly what Earth needed, because those asteroids and comets weren't just delivering water, they were also bringing something else: the building blocks of life, organic compounds, amino acids, the molecular ingredients that would eventually combine to create living organisms. Scientists have analyzed meteorites that fall to Earth today. Many of them, particularly carbonaceous chondrites, contain complex organic molecules. Over 70 different amino acids have been found in these space rocks. That's far more variety than life on Earth uses. These molecules formed in the cold depths of space, where they were protected from the harsh radiation of the sun, and they were delivered to Earth by the billion-ton throughout the late heavy bombardment. But here's the puzzle. How did these delicate organic molecules survive the violence of the impacts? When an asteroid hits Earth at 20 kilometers per second, it releases enough heat to vaporize rock. Surely that would destroy any organic compounds, right? For years, scientists thought the bombardment destroyed any hope of life. That Earth would have to wait until the impact stopped before life could begin. Then, researchers started doing experiments. They fired projectiles at targets containing organic compounds, simulating asteroid impacts. And what they found was astonishing. While the surface of the impact site gets hot enough to vaporize everything, the interior of the asteroid stays relatively cool. The organic molecules inside are protected, cushioned by the outer layers that absorb the impact energy. When the asteroid shatters, these molecules are scattered across the landscape, intact and ready to participate in chemistry. Even more remarkable, some impacts might have actually helped create life's building blocks. When an asteroid hits the ocean, which covered most of Earth's surface, it creates specific conditions: high pressure, high temperature, and a rich mixture of chemicals. These are exactly the conditions needed for certain organic synthesis reactions. The impact itself might be creating amino acids and other complex molecules. So the late heavy bombardment wasn't just destruction, it was also creation. Each impact was both an ending and a beginning, destroying what came before while simultaneously delivering the ingredients for what would come next. This is the paradox at the heart of Earth's story. Violence and creation are not opposites. They're partners in the cosmic dance that made our world. But while the surface is being pummeled, something equally important is happening deep inside Earth, something that will prove absolutely crucial for life's survival. Remember that when Theia collided with proto-Earth, Theia's iron core merged with Earth's core. This added mass to Earth's interior, making our planet's core larger and hotter than it would have been otherwise. That core is a ball of molten iron and nickel, roughly the size of Mars, sitting at the center of Earth. The temperature there exceeds 5,000 degrees Celsius, as hot as the surface of the sun. And it's not sitting still. The outer core is liquid, and it's churning constantly, driven by heat from the inner core and the slow cooling of the planet. This churning creates currents in the molten metal, swirling flows that stretch from pole to pole. And here's where things get interesting. When electrically conductive material moves, it generates a magnetic field. It's basic physics. A flowing liquid metal is essentially a giant electromagnet, and that's exactly what Earth's core is. The churning molten iron generates Earth's magnetic field, an invisible shield that extends thousands of kilometers into space. We call this process the geodynamo. Without the giant impact, Earth's core might not have been large enough or hot enough to power a strong magnetic field. Theia's contribution was essential. That cosmic violence, that planetary catastrophe, gave Earth the magnetic shield it needed to survive. Because here's the thing, a magnetic field isn't just interesting. It's absolutely vital for life. The sun doesn't just emit light and heat, it also spews out a constant stream of charged particles called the solar wind. This wind travels at over 1 million kilometers per hour, carrying enough energy to strip away a planet's atmosphere molecule by molecule. We can see this happening right now on Mars. Mars lost its magnetic field billions of years ago, and the solar wind has been steadily eroding its atmosphere ever since. What was once a thick, warm atmosphere is now thin and cold. Earth's magnetic field deflects the solar wind, creating a protective bubble around our planet called the magnetosphere. When solar wind particles hit the magnetosphere, they're redirected around Earth, flowing past us like water around a rock in a stream. Some particles get funneled down to the poles, where they collide with atmospheric molecules and create the aurora borealis and aurora australis, the northern and southern lights. These beautiful displays are actually visible evidence of our planet's magnetic shield in action. Without this shield, Earth would have suffered the same fate as Mars. The late heavy bombardment would have been the least of our problems. The solar wind would have blown away our atmosphere in just a few 100 million years. The oceans would have evaporated. Any life that managed to start would have been sterilized by radiation from space. Earth would be a dead world, cold and barren, all because we didn't have a magnetic field. But we do have one, thanks to Theia. Thanks to that violent collision 4.5 billion years ago that gave Earth a large, hot core capable of generating a powerful magnetic field. Once again, we see how cosmic violence didn't just shape Earth, it made Earth livable. The late, heavy bombardment finally ends around 3.8 billion years ago. The impacts don't stop completely, but they become much less frequent. Earth finally has time to cool down, to stabilize. The crust solidifies into something resembling permanence. The oceans stop boiling. And in those oceans, something miraculous is about to happen. But before life can emerge, Earth needs one more thing: a way to recycle its crust, a way to regulate its temperature over billions of years. It needs plate tectonics. Plate tectonics is unique to Earth. No other planet in our solar system has it, and it's driven by violence. Deep within Earth's mantle, radioactive elements decay, generating heat. This heat has to escape somehow. It rises through the mantle in massive convection currents like boiling water in a pot. When these currents reach the surface, they push against the crust from below. The crust isn't one solid shell. It's broken into pieces called tectonic plates. These plates float on the semi-molten mantle like rafts on a slow-moving river. Where the mantle currents rise, the plates are pushed apart, creating rifts. Molten rock wells up from below, solidifying to create new crust. This is happening right now at mid-ocean ridges, underwater mountain ranges where new ocean floor is constantly being born. Where the mantle currents sink back down, plates collide. And this is where the violence happens. One plate is forced beneath another in a process called subduction. The descending plate is dragged down into the mantle, where it melts and is recycled. This recycling is essential. It removes carbon dioxide from the atmosphere by dragging carbonate rocks down into the mantle. It regulates Earth's temperature, preventing a runaway greenhouse effect. The collision zones are anything but peaceful. Enormous pressures build up as the plates grind against each other. When the pressure finally releases, the result is an earthquake. The most powerful earthquakes can shift entire coastlines by meters. They can trigger tsunamis that cross entire oceans. The 2011 Tohoku earthquake in Japan was so powerful, it moved the entire island of Honshu 2.4 meters to the east and shifted Earth's axis by 10 centimeters. Where oceanic plates collide with continental plates, something even more dramatic happens. The oceanic plate, being denser, plunges beneath the continental plate. But as it descends, water trapped in the rocks is released. This water lowers the melting point of the mantle above it, creating pockets of magma. This magma, being less dense than the surrounding rock, rises, and when it reaches the surface, it erupts. A volcano is born. The Ring of Fire, a horseshoe of volcanoes encircling the Pacific Ocean, is a monument to this process. Over 450 volcanoes mark the boundaries where plates collide and subduct. Mount Fuji, Mount St. Helens, the Andes Mountains. All born from plate collisions. All products of violence. And this violence isn't ancient history. It's happening right now, beneath your feet. Volcanic eruptions are among the most destructive forces on Earth. The 1815 eruption of Mount Tambora ejected so much ash into the atmosphere that it blocked out the sun, causing the year without a summer. Crops failed worldwide. People starved. The 79 AD eruption of Mount Vesuvius buried the Roman cities of Pompeii and Herculaneum under meters of ash, preserving them for millennia. These catastrophes remind us that Earth is still a violent place. But here's what's remarkable. This violence is exactly what makes Earth habitable. Without plate tectonics, without volcanic eruptions, Earth would have suffered a fate worse than Mars. Let me explain why. When life began on Earth, the atmosphere contained huge amounts of carbon dioxide. This created a powerful greenhouse effect, keeping Earth warm. But over billions of years, living organisms have pulled carbon dioxide out of the atmosphere, incorporating it into their bodies and eventually into rocks. This is a problem. As carbon dioxide levels drop, Earth should cool. Eventually, it should freeze completely into a snowball Earth scenario where ice covers the entire planet from pole to pole. And once that happens, it's almost impossible to reverse. The ice reflects sunlight back into space, making the planet even colder. It's a runaway freezing effect. Earth should have frozen solid billions of years ago, but it didn't. Why? Because of volcanoes. When tectonic plates subduct, they carry carbonate rocks down into the mantle. These rocks melt, releasing carbon dioxide. That carbon dioxide rises with the magma and is released into the atmosphere during volcanic eruptions. This is Earth's thermostat. When the planet gets too cold, volcanic activity pumps carbon dioxide back into the atmosphere, warming things up again. When it gets too hot, weathering pulls carbon dioxide back out. This carbon cycle, driven by plate tectonics and volcanic violence, has kept Earth's temperature in the habitable range for billions of years, long enough for life to emerge, evolve, and eventually produce us. Without this violent recycling, without the subduction and eruptions, Earth would be frozen solid. Plate tectonics didn't just shape Earth's surface, it made long-term life possible. And Earth needed that long-term stability because life didn't emerge immediately. Despite having oceans, an atmosphere, and organic molecules delivered by asteroids, life took time. The earliest evidence for life dates to about 3.8 billion years ago, right after the late heavy bombardment ended. These first organisms were simple, single-celled bacteria and archaea, living in Earth's oceans, feeding on chemical energy. But they were life, and their existence proves something profound. When conditions are right, when you have liquid water, organic molecules, and energy sources, life emerges quickly, geologically speaking, almost immediately. This suggests that life might be common in the universe, that on any planet with the right conditions, life will eventually appear. But here's the sobering part. Those right conditions are incredibly specific, and almost all of them trace back to cosmic violence. Earth needed the giant impact to create the Moon, which stabilizes our axial tilt and gives us seasons. Earth needed the impact to strip away the primordial atmosphere and give us a fresh start. Earth needed Theia's core to power our magnetic field and protect us from solar wind. Earth needed the asteroid bombardment to deliver water and organic molecules. Earth needed enough radioactive elements in the mantle to drive plate tectonics, which regulates temperature and recycles nutrients. Every single one of these requirements came from violence, from catastrophes on a planetary scale, and they all had to happen in just the right way, at just the right time. This realization changes how we think about the search for habitable planets. We've discovered thousands of exoplanets orbiting other stars. Some are in the habitable zone, the region where liquid water can exist. But being in the habitable zone isn't enough. A planet needs the right size to maintain plate tectonics. It needs to have suffered the right kind of giant impact to have a large moon and a protective magnetic field. It needs to have been bombarded with water-rich asteroids, The odds of all these things happening to one planet are staggeringly small. It's like winning the cosmic lottery. And Earth won. This might explain the Fermi paradox, the question of why we haven't detected alien civilizations despite the vast size of the universe. It's not that life is impossible. It's that Earth-like planets, planets that have experienced the exact sequence of violent events necessary to support complex life, might be incredibly rare. Or maybe we're just the first. Maybe we're living in the early universe, and Earth is one of the first planets to get everything right. In billions of years, the galaxy might be teeming with life. But right now, in this moment, we might be alone, uniquely positioned as the universe's first witnesses to its own existence. That's both humbling and terrifying. But whether we're alone or not, one thing is certain. We are children of violence, of every atom in your body was forged in the nuclear furnace of dying stars that exploded billions of years ago. The iron in your blood came from a supernova. The calcium in your bones was created in the death throes of a massive star. You are literally made of stardust. And the planet you stand on was assembled through countless catastrophic collisions. The water you drink was delivered by asteroids traveling at thousands of kilometers per hour, impacting with the force of nuclear weapons. The air you breathe was exhaled by volcanoes, driven by the violent churning of Earth's mantle. The ground beneath your feet is riding on tectonic plates that collide and grind with enough force to level mountains. Violence isn't separate from Earth's story. Violence is Earth's story. And that violence continues. Right now, as you watch this, tectonic plates are moving. Millimeters per year, but moving nonetheless. Earthquakes are releasing tension built up over decades or centuries. Volcanoes are erupting, adding new land to the planet. Asteroids are burning up in the atmosphere. They're descendants of the same bombardment that brought us water and life. The moon is slowly drifting away from Earth, receding at about 3.8 centimeters per year. Billions of years from now, it will be so distant that it can no longer stabilize Earth's axial tilt. Our seasons will become chaotic, swinging wildly from extreme to extreme. Eventually, Earth's core will cool. The magnetic field will weaken and fade, and the solar wind will begin eroding our atmosphere just as it did on Mars. But that's billions of years away. For now, we exist in a golden moment, a brief window when Earth is perfectly tuned for life, when the violence that created our world has settled into a balanced rhythm, when the chaos has organized itself into systems that support not just life, but conscious life. Life that can look up at the stars and wonder where it came from. And now you know the answer. You came from violence, from colliding planets and shattering asteroids, from erupting volcanoes and shifting continents, from the cosmic demolition derby that was the early solar system. That violence didn't just create Earth. It created the conditions for every living thing that has ever existed on this planet, including you. So the next time you look up at the moon, remember, that beautiful object in the night sky is a monument to the most violent event in Earth's history. The next time you feel an earthquake or watch a volcano erupt, remember, that's not a catastrophe. That's Earth's life support system at work, maintaining the delicate balance that allows you to exist. The next time you drink a glass of water, remember, that water traveled across the solar system on a chunk of rock and ice that exploded with the force of a nuclear weapon when it hit Earth. We are not separate from the violence that created Earth. We are the continuation of it, the universe expressing itself through us. We are cosmic violence that learned to think, to wonder, to create. And that might be the most remarkable transformation of all. That destruction could become creation. That chaos could become order. That violence could become life. Earth's story is not finished. The violence continues, though in more subtle forms than the planet-shattering impacts of the past. And life continues, adapting, evolving, becoming ever more complex. We are living in the middle of Earth's story, not at the end. And what comes next depends partially on us, on whether we can learn from the violence that created us and choose a different path forward. Because if Earth teaches us anything, it's this: violence can create, but so can cooperation. The atoms in your body came from dying stars, yes, but they only came together because of the gentle accretion of dust grains in the solar nebula. The slow, patient process of building something from nothing. Earth needed both: the violence to create the conditions for life, and the calm to allow life to flourish. Maybe that's the lesson: that creation requires both destruction and preservation, both chaos and order, both violence and peace. Earth found that balance, and in doing so, it created a world where life could emerge, where consciousness could arise, where beings could exist that are capable of understanding their own origin story. You are standing on a miracle. A planet that shouldn't exist, born from catastrophes that should have rendered it uninhabitable. But instead, through an improbable sequence of violent events, each one perfectly timed and scaled, Earth became the most precious thing we know of in the universe. A living world. Home.